Okay, well, maybe we should get started. So until recently, there was a tradition that local speakers needed no introduction, which I think is an excellent idea. So my goal here is to attempt to embarrass Vikram enough that he'll petition the division for return to former tradition. So New York Magazine declared 2022 the year of the Nepo baby. So for those of you not familiar with Nepo babies, it comes from nepotism, and a Nepo baby is the offspring of a famous person who follows their parent into the creative industry and often has success and competition. So Nepo babies, as you know, were very common in Hollywood, banking, real estate, from fairly obscure ones to ones that today might be a source of intellectual information, classifies as platinum grade Nepo babies who come from famous parents that are major players in their own right now. So Donald Trump, the Rockefellers, Michael Douglas, Miley Cyrus, Jane Fonda, Drew Barrymore, etc. And there are a few platinum grade Nepo babies in physics. So John Herschel, the third and fourth Lord Raleighs, Owen Bohr, Lawrence Bragg, Elaine Curie. So Vikram too is well on his way to becoming a platinum grade Nepo baby. And I presume I was asked to introduce Vikram since I've known his mother, Lakshmi Sarvepalli, radio astronomer since before he was born. And his father, Ravi Subramanian, formerly of the Narabri Observatory and director of the Raman Research Institute, is also a famous radio astronomer who has, among other things, a long history of collaboration with Caltech faculty on radio afterglows of gamma ray bursts. Now, since I'm not Sri Kulkarni, I would emulate Cicero and say, multa praetereo. I pass over many stories that Dr. Sarvepalli has told me at various conferences on radio sources in AGN in the 1990s and 2000s about the difficulties of maintaining a career while raising a very active, curious, and somewhat troublesome son. So Vikram was an undergrad at the Australian National Observatory, got his bachelor's in physics in 2009. He spent a year at CSIRO with George Hobbs and Dick Manchester working on pulsars, and then a year at UC Berkeley and Charlie Towns' group working with the infrared spatial interferometer on Wilson, just a few miles from here, studying the red supergiant and Orion's right soldier Betelgeuse. So if there are any undergrads in the audience wondering if it's okay to take a gap year or two, the answer is yes, it's okay. Then Vikram began his PhD at University of Melbourne, which he got in 2014 on pulsar timing array searches for gravitational waves from merging supermassive black holes, where he worked with Stuart Wyeth on the theory side and George Hobbs on the experimental side. Then we were lucky to get him to Caltech as a Millikan Fellow, and he got into the hot new field of fast radio bursts. In 2018, he became a Clay Fellow with the Harvard Smithsonian Center for Astrophysics, and then joined the Caltech faculty a year later in 2019. And today he'll tell us about the Deep Synoptic Array, the origins of fast radio bursts, and I see that he has on slide 1 out of 90. So
Thanks, Bill. I've got the petition ready to go here as well. Thanks, everyone. Thanks for coming. It's my pleasure to tell you a little bit about what I and my group have been doing for the last few years here at Caltech. I joined here again as faculty in 2019. It's been an interesting few years, to say the least. But I just wanted to start by giving you a sense of my broader interests. I generally like to think somewhat schizophrenically, both in terms of the very compact as well as the very diffuse. I care a lot about compact objects, neutron stars and black holes, as well as the most diffuse, tenuous, hard to observe structures in the universe, the intergalactic medium, dark matter, and so on. And I like to do this by using various types of radio telescopes. So over here at the bottom of the one, I'll be telling you about the Deep Synoptic Array 110 antenna instrument at Owens Valley. And I'm particularly excited about this one up here on the left, which is currently trying to observe the star DQ Tau, which we hope will flare in the millimeter band, and is generally an experiment in millimeter time domain astronomy. So broadly speaking, compact objects, diffuse matter, as well as experimental radio astronomy. I'd also like to really, extend a very heartfelt thanks to the amazing students and postdocs who've worked with me over the years, the 4-ish years now. And I'll be highlighting the work of various people here throughout the talk as well. One person in particular I want to highlight is Dana Simard, who was a postdoc with me for 3 years and was really critical in making the DSA work as it is today. So, rather than trying to say everything about everything, I'd like to really focus us in on a very specific question, the origins of fast radio bursts. So this is not a fast radio burst. This is the kind of data in which we observe them. So what we're looking at here are time series of radio spectra in the gigahertz band obtained at sub-millisecond cadences. And in these sort of data, if you're very lucky, you happen to see things that look like this. So this swept frequency signal is a fast radio burst. Played a bit more slowly, what you see is that it starts off at high frequencies and then quadratically sweeps down to lower frequencies. And this, as it turns out, is due to dispersion in both interstellar as well as intergalactic plasma. And so when you sort of try and count up the amount of delay in different frequencies and relate that to the amount of plasma between us and the source, what we find is that the amount of plasma is a lot more than expected from the Milky Way. And so what we then do is we say, we think the universe is essentially entirely ionized at low redshifts, count up the total sort of cosmic baryon density, and then ask roughly how far away are the sources. And we typically get distances of gigaparsecs, so well beyond the Milky Way. And this is why I'm very excited. We know of nearly 3,000 radio pulsars within the Milky Way today that look like this, but these sources are special because they come from well beyond the Milky Way. So, in some more detail, what these bursts look like can be relatively easily summarized as follows. So we have the high dispersion greater than expected from the Milky Way column. We have energy scales on the order of 10 to the 40 erg. These release a massive amount of energy in these sort of microsecond to tens of millisecond timescales. Of course, these timescales are when you correct for the dispersion effect to get pulse profiles that look like these. We also, in many cases, see very complex time and frequency and polarization structures. This particular burst, for example, has a significant amount of Stokes-V circular polarization as well as linearly polarized intensity. And we have a rate of events of somewhat over 1,000 over the entire sky every day, which when you relate to the cosmic volume is something like 100,000 per cubic gigaparsec per year, which is a special number because that is how often a supernova goes off in the universe as well. So what can we learn then just from this sort of information? Well, one, you can sort of try and take the time and energy scales and relate it to something to do with the source properties. The time scale corresponds to sort of a few hundred, potentially a few thousand kilometer scales at the source. We've observed scales well under a microsecond in some cases, which is very interesting in terms of light crossing times. We also then need to get the radiation out of the source environment, which is difficult, for example, from an active galactic nucleus. And finally, we need to sort of explain the existence of both actively repeating sources as well as sources we haven't yet observed to repeat. There's an incredibly rich phenomenology that can be summarized in these relatively straightforward points. These all point towards a likely neutron-star origin. If we take the energy densities, if we take the brightness temperatures, we get a coherent source that is extremely small. A neutron star appears to fit that. If we take the need to have these things be relatively clean, a neutron star fits that as well. And then if the third point is less straightforward, but at the very least, we know that neutron stars don't spontaneously explode when they emit a pulse. They are in some sense persistent sources. And so this all together points towards something like a neutron star as the origin. So far, so good, right? But there remain some really fundamental questions, as you'll see throughout this talk. The first one is, sure, we might think, based on these sort of circumstantial heuristic arguments, that a neutron star is the source of FRBs. But what sort of neutron stars? Have we seen them in the Milky Way? Are they special or not? What possible physical mechanism can result in such extreme release of energy that we haven't yet observed, at least commonly, from known neutron stars? Also, there's a very interesting and exciting use of FRBs, which is to probe matter along the sightlines to which they propagate. So this is a great animation from Lee and Connor showing the accrual of dispersion measure as an FRB propagates through a slice from the illustrious cosmological simulation. So the background shows baryonic structures generally collapsed and associated with collapsed structures like clusters, groups, and individual galaxies. And the giant jump in the middle indicates the passage of this particular FRB through a galaxy cluster. And so various cosmological structures leave their imprints on the FRBs we observe. The dispersions we observe are due to the sort of combination of all the various halos, filaments, and indeed voids that the FRBs pass through. And so this matter is extremely hot, very hard to observe in its entirety. Indeed, over 80% of baryons in the local universe form this state of matter. And FRBs see them all. They're impacted by the entire columns of this matter. And so we care a lot about the distribution of baryons, especially in the low redshift universe, as well as how galaxies form out of the intergalactic medium and serve to modify it. So this is I wanted to expand this point a little bit because the reasons why we care about the source of FRBs are kind of clear. It's obviously a compelling problem to understand how such extreme forms of emission can exist. But the second point is something that's only just beginning that we're hoping to really pioneer here at Caltech. This is a animation from the original illustrious simulation showing dark matter density on the left, gas temperature on the right. And this really tells an amazing story of how galaxies form out of the intergalactic medium, serve to modify it through, for example, these amazing sort of episodes of slow radio mode feedback into the IGN due to slowly accreting supermassive black holes. If you really squint, you sometimes see some flickering points at the centers of the nodes of this web. Those represent bright quasars. This picture is really detailed and great and shows, we think, the evolution of cosmic structure, and yet we know it's almost certainly wrong. The picture, the prescription for how galaxies affect the IGM in this particular simulation is almost certainly wrong and is indeed superseded by future iterations. There are at least 5, likely more, such simulations today that, among themselves, disagree quite strongly on the exact structure, the distribution of densities, the distribution of temperatures, the evolution of how these things change through cosmic time of matter around and in between galaxies. FRBs can test these models. So this is, we really want to get into science, right? But it turns out that it's really, really hard to do it. And it's actually not that hard to detect an FRB. Telescopes today are detecting an FRB, a few FRBs a day. I think I noticed 2 or 3 alerts just today from the China telescope in Canada. And this is totally amazing. I mean, this plot shows, I believe, 535 FRBs detected by the China telescope just until 2019 or something like that. FRBs have been detected, they're falling out of the sky, more than 1,000 go off every day. But each of these is only localized to an area approximately the size of the full moon. You cannot associate these with an individual galaxy unless by some chance a galaxy happens to be Andromeda or something really close. And so the real challenge is to try and take even just a few of these FRBs and localize them with pinpoint accuracy to individual galaxies. Now, this is hard for the following reasons. First, if you assume some sort of a rate distribution that looks like this is roughly correct. What you find is that in order to detect roughly one per month, you need the sensitivity of a radio dish 40 meters in diameter, with a field of view of one that is just 15 meters in diameter, and the angular resolution of the radio dish a few kilometers in diameter. And this is just a function of d squared, and lambda over d, and so on. These are not complicated statements. This is really hard. You need to excel along axes of sensitivity, field of view, localization accuracy, as well as the ability to go really fast. Observe the sky on millisecond timescales in order to see these things. This is why this problem has been a real challenge for the field so far. The way we do it, of course, is using radio interferometers. The radio interferometers are very much like a broken mirror. Instead of building a few kilometer-sized telescope, we populate a few kilometer-sized areas with radio antennas, and then combine them in order to make images. We do this by sensing the spatial coherence function of the incident electric field, and then invert that using the Fourier transform relationship advantage of the Zanicki theorem in order to get images of the sky. This, of course, is not a perfect process. As you appreciate, if you have an array like the VLA, you end up with a PSF, a point spread function, that is that of an incredibly bad mirror, right? It's a Y-shaped mirror, and it looks something like this. But of course, when you then deconvolve that PSF from your image, you're able to recover true structures in the sky. And so what we want to do is build radio interferometers that can have these wide fields of view, sensitivities, localization accuracies, and time resolutions to discover FRBs. So this the state of play at the start of the story in 2017 was that this had been done exactly once. And at one time was absolutely amazing. So there was this burst that in 2016 was discovered to be a repeating source of FRBs. And then various people around the world, collaborating as part of the European VLBI network, turned a whole bunch of different telescopes at this repeating source, and just happened to catch a whole bunch of bursts from the source, and were able to localize it to millisecond accuracy in the sky. The bursts were detected at Arecibo, a giant telescope in Germany called Effelsberg, South Africa, across Europe, all the way through to Western China. And they were able to combine all this information to localize the burst to around millisecond accuracy to a really interesting galaxy. So the galaxy turned out to be this dwarf, rapidly star-forming galaxy. Indeed, the specific star formation rate, something like nearly 1,000 times that of the Milky Way. And the amazing thing about this galaxy was that it was entirely not what we expected for FRBs at all. We also happened to observe an incredibly high Faraday rotation measure along the direction of the source, one of the highest Faraday rotation measures ever observed. This, of course, refers to line of sight magnetic fields, causing the polarization position angle to rotate as a function of frequency. The fields that were detected here were more than 10 to the 4 times larger than typical interstellar magnetic fields. This rotation measure also changed by nearly a factor of 2 over a few years, indicating that the magnetism was entirely concentrated locally to the source. And to add to the story, this thing was also coincident with a radio synchrotron source. Indeed, we believe that the burst originates from within this radio synchrotron source, and that the same magnetic field that result in the synchrotron emission are also Faraday rotating the radio emission from the FRB. And the synchrotron source itself had a rather unusual spectrum, and so on and so on. The yield from this one event was truly amazing. After one event, people were publishing concordance models of FRBs that involved at least 4 different layers, one causing the FRB, one causing the barrier rotation, one causing the dispersion, one causing the multi-part propagation, one causing dispersion, and so on. Truly amazing stuff. Authors one of them. Yes.
Do you know about the units of the rotation measure? So
Yes.
From here, I see like radian per meter squared.
Exactly.
What do you expect per meter?
So the change in
A
the
smaller number.
so yeah, the change in the polarization position angle is a frequency squared effect. And so we quantify it as the amount of rotation in angle per meter squared in wavelength. And so, for example, if you have, so we also quantify the dispersion in units of parsec centimeter minus 3, so the column density. 1 unit of dispersion and 1 unit of these units of rotation measure corresponds to a magnetic field strength of about 0.8 microgauss. These dispersion measures are typically of order a few hundred. That gives you a sense of the scales. So really the point I want to make is this, that identifying the origins of FRBs really does require these representative samples of accurately localized events. We need to have a reasonably large sample that tries to capture the diversity in the sources of events localized to individual galaxies, and preferably in some cases to regions within those galaxies. We also really need this in order to do all the science we're interested in terms of the propagation of FRBs through the circum-galactic and intergalactic medium. We need to be able to characterize the individual sightlines, relate the amount of dispersion to individual structures along the lines of sight. And I'll show you examples of that a little later as well. So, how do we do this? Well, this is really accomplished through the Deep Synoptic Array program. And so Greg Hellman initiated this in 2013 with the very first prototype antenna, that is Sandy Weinreb, standing there, who's been instrumental to this program from its inception. We then, when I arrived here as a postdoc, built DSA-10, I believe still was there during the completion of construction of this at Owens Valley, and saw a lot of shoveling happening at the time. We got this operational in 2017, and I'll say a bit more about that. This led directly to STARE 2, where we took 3 of the receivers, 3 of the receiver chains from DSA-10, put them at 3 different locations around the Southwest US, and we're looking for very bright events. We took the receivers and pointed them up, not at dishes. We then were able to nearly complete DSA-110. I'll say a lot about that a little later in the talk. And then I'm going to say nothing about this one at all, and a little bit about DSA-2000 at the end. So, DSA-10. So this is a really, I really like the story because I think it's a great example of what one can do here as a postdoc. So I came here in 2015 with this, having just discovered a really, really bright FRB. I believe there's a picture of it outside Fiona's office. It's amazing spectrum. We then had this idea that, hang on, if we've seen just one bright FRB, maybe there'll be a few more. Sri Kulkarni at the time said, of course not, there's no chance of this. Don't you know about radio source counts being Euclidean and the flux density proportional to f-3 halves? You've got no chance. But then we thought, hang on, what's the source count of flat? Anyway, let's just do this, right? And so we were able to, through a PDRDF award, get these dishes. I ordered them from Alibaba.com for $1,700 per dish, including shipping. We assembled them at Owens Valley. Sandy Weinreb was key in designing a signal chain for this thing. This shows our extremely sophisticated range test of the feed. Those with very sharp eyes will notice that the front of the feed consists of 2 choke rings, which are made up of actual cake pans. A company called Fat Daddy-O's. These are again, very sophisticated equipment. We spent a lot of time thinking about how to position the antennas. We had 10 of them on the old millimeter array baseline at Owens Valley, the last one sitting over here near the site opposite, yielding this PSF. And this is what 4 dishes look like. And we were fortunate enough, within about 6 months of observing, to discover an FRB, which remains the most luminous FRB known so far. This shows the dispersed dynamic spectrum and the pulse profile up there. This movie in the middle that's playing, looping over, is about a half a degree image at about 130 microseconds per frame. And in the middle of it, you see this the PSF shape appear, indicating the occurrence of the FRB. And it turned out this thing was likely associated with a galaxy at redshift 0.66. This was sort of co-discovered with a burst from the ASCAP telescope in Australia as the next 2 localizations after that initial one I discussed earlier, the repeating FRB. And what was particularly interesting about this was that this is not a dwarf galaxy. This is a Milky Way-like galaxy with a Milky Way-like star formation rate, and of course, it's a lot further than 1 gigaparsec. It actually turned out to be very interesting. I don't want to dwell on this much, but just to say that the actual field of this thing, this one being the host, was quite fascinating in that we just so happened to have a quasar sitting behind it. I believe George obtained the spectrum, and were able to detect magnesium-2 and absorption at both the redshift of this host galaxy as well as to a pair of intervening galaxies along the sightline. And we're able to then set a limit on the ratio of the ionized to neutral hydrogen scaling up from magnesium-2 along the sightline, which is very nicely consistent with other limits from the literature. This, of course, telling something about our understanding of how much neutral versus ionized gas there is in these halos. Very approximate work, but tantalizing nonetheless, and something that we hope to pursue in greater depth in the future. Anyways, this is great. This took us through to late 2019. Of course, COVID hit in 2020, and as you'll see in a little while, this caused us to pause construction of the successor array, the DSA-110. During this time, however, something rather incredible happened. So, just the background for this, a graduate student who working with me at the time, Chris Chenek, had been previously working with Shri and had set up this array called STARE-2 with the goal of discovering the sort of low end of the FRB energy distribution. So this plot shows duration versus luminosity of a whole range of different types of radio transients. And the FRBs are clearly distinct from pulsars and other known neutron-star emission in their energetics. And so, of course, the obvious question is, what does the low end of this look like? And this is difficult, of course, because either you need incredible sensitivity or you need to look really nearby, and Chris chose to look really nearby. The problem being that if you want to look within the Milky Way, the rate of less than 1 per century is not amenable to finishing your graduate thesis in a reasonable time. And so we decided nonetheless to proceed with an extrapolation of the rate down by nearly 2 orders of magnitude. And so Chris put together this instrument consisting of 3 of the DSA-10 signal chains and software backends situated near Delta, Utah at a cosmic ray detector site, one at Owens Valley and one at NASA Goldstone. And the idea being that by using time of flight measurements between different stations, we're able to provide crude localization of the bursts in the sky, not interferometry, but pure time of flight measurements. And we were fortunate enough to actually see something. So on April 28th in 2020, the CHIME telescope in Canada, a very large 80 by 100 meter 1024 receiver radio instrument in British Columbia, reported the detection of a burst very, very far from its optical axis, so in a far side lobe of its response. And they were very excited because this particular burst was probably very bright and also potentially associated with a known galactic magnetar. Magnetars being the most magnetized known neutron stars with fields over 10 to 14 Gauss, powered by the decay of the field and not by rotation. And amazingly enough, we actually saw the same thing at all three stations. And what was critical about this was that we were able to, because it wasn't off axis for us, actually measure the true flux density of this burst and show that it really was identical to extragalactic FRBs. And so we were also able to localize it using the 3 time of flight measurements and 3 baselines to a region containing this known magnetar. And amazingly enough, this same burst was also detected in X-rays from a constellation of space-based instruments. And this burst turned out to actually be precisely coincident in time to the radio burst as well. This had been potentially predicted by some models of emission from FRBs, not by others, and so it formed a very interesting constraint. And it was also interesting that the coincident burst was unusually hard in its X-ray spectrum. But nonetheless, the bottom line was that we had found a potential source of FRBs, a galactic magnetar. And the suggestion, of course, being that if these sources make FRBs, then maybe we've found the source of FRBs, maybe we're done, end of story. As it turns out, that's not quite the case. It's also the case now that this particular magnetar has emitted a larger range of bursts, and extragalactic sources of FRBs have also been found that are somewhat less luminous than even this magnetar. This continuum between galactic pulsars and extragalactic FRBs is now steadily being filled in. But yes, we found a potential source of FRBs. Which brings me to the DSA-110. So the DSA-110 is what I've spent most of my time on these last few years. And it is an extensive array of radio antennas, 4.65 meter diameter dishes situated at Owens Valley. The core consists of 95 antennas coherently combined for FRB detection, accompanied by 15 outrigger antennas spread out over the valley floor to enable accurate localization. So the DSA-110 is currently in its latter stage of commissioning. We anticipate construction to be finished later this summer. We currently have 63 antennas fully operating, with about another 10 that have been built but not incorporated into the array. I only want to acknowledge the massive team that's gone into getting us to the stage, especially the Owens Valley staff who worked through a lot of COVID in rather trying and difficult conditions. We had a situation where there was one staff member per building at one stage. And so a lot of our digital backend, for example, consisting of 24 servers, 40 FPGA boards, and a whole lot of, 486 fiber splices, was all done by one person working alone in a basement for months. It's really incredible construction effort. And so the requirements that we placed on this array to begin with were rather stringent. We required that we had this wide field of view. Recall that I said that roughly a square degree with large sensitivity gets you 1 per month. We wanted to have a bit larger field of view than just a square degree. We wanted higher time resolution, angular resolution better than a few arc seconds, and excellent calibration as well. And this is enabled by some key technological innovations, one of which I want to really focus on being the receivers, which Sandy Winder and his group were able to build from scratch here, and which deliver noise temperatures of around 7 Kelvin at room temperature. And so these receivers do not require cryogenic cooling, unlike those at other telescopes, and that enables us to have the sensitivity we need. This is enabled by a combination of this really great low loss input matching network, as well as a transistor designed to work at several hundred gigahertz frequencies, being used at around gigahertz. So the timeline's roughly like this. We were funded in late 2018, had a lengthy design phase to enable these innovations. We're all poised for construction at the start of COVID, but took a few month pause due to a full shutdown. We then slowly but surely started laying out antennas, receivers, digital backend, while the team was writing all the software from our houses here. And then we're now in commissioning with a limited array, with a full array expected again in summer. And for most of the rest of the talk, I'm going to tell you about some of the early results from DSA-110. But first, things didn't look so good at the start of commissioning. This was from February last year, photos taken overnight at Owens Valley, where a fire swept through the valley. Right at the start of commissioning of DSA-110, and there was a few hour period where we didn't know whether the whole observatory was in flames or not. Certainly, some satellite imagery showed the observatory was in flames, and as it turned out, you can see a DSA antenna there, and the flames probably, if I'm not mistaken, about 50 meters away from that antenna. But thanks to some amazing work by a whole bunch of local fire services, they were able to sort of dig a protective perimeter and then air tankers the following morning, put the fire out, and all was good. And we started observing. And so, how does this work? So this is an example burst from DSA-110. This shows the spectrum and the time series. And what we do is when we detect something like that, we trigger the storage of electric field data, what we call the voltage data, from the whole array to enable the localization. So what we do then is we use calibrators in both out of the field as well as in the field to sort of adjust the responses of each of the antennas in order to get full coherence. We then do an asymmetric correction using nearby very accurately localized calibrators. And then we image and fit the position of the FRB itself. And finally, are able to derive an uncertainty from the various components, the dominant component typically being the signal-to-noise ratio of the FRB itself. And so what you can see here is the PSF, the raw FRB image, the image after getting rid of the PSF, involving the PSF, and finally an illustration of the accuracy, in particular for these very accurately localized calibrated sources. So here are the first 36 localizations that DSA-110 has delivered. These are the little sort of indicators show the positions of each of the FRB sources. I've sort of overlaid them on archival optical images of these regions for the Pan-STARRS survey, and tried to get the color schemes to show a galaxy if it is present in the survey. The images from top left to bottom right are ordered in increasing extragalactic dispersion measure. So this is the amount of dispersion contributed beyond the Milky Way, which, if all host galaxies are the same, would be an indicator of distance up until the sort of natural cosmic variance in different sightlines through the intergalactic medium.
But this doesn't have any host estimate, it just has the Milky Way.
That's right.
So
Yep.
there's one in -22.
That's right.
The error in the Milky Way.
Exactly, yes. The top one with a negative 22 extragalactic DM represents the nearest one we've found. That is the arrow roughly in the Milky Way models. So a few things to note here. Typically the ones up here tend to have brighter host galaxies than the ones down here, but there are clear and very interesting exceptions to that rule. For example, this one and this one and this one are interesting exceptions. This one is very interesting, and we'll talk a bit more about those in a minute. But I want to go through a few of the results that we're finding from this sample so far. But I really want to emphasize that this is very new territory. We've nearly doubled the number of localizations from all the other telescopes worldwide combined. And so we were in the regime of very small number statistics, and we're now in the regime of small number statistics, hopefully growing this to reasonable statistics in the future. But there are some sort of features of this data set that are really already telling us something about what we may expect to find. So first of all, this one up in the top left is so far the nearest localized sort of non-repeating FRB. And it turned out to be very interesting because of that negative 22 apparent extragalactic DM. Because when you really try and work at the sort of Milky Way sightline along the line of sight, you find it's very, very hard to have much dispersion measure outside the Milky Way along the sightline. It's very hard to have anything resembling most models for extragalactic DM, especially in the Milky Way halo. And so we were able to put a very interesting constraint, at least along this sightline, on the dispersion through the Milky Way halo, which, if you combine, which is consistent with recent constraints also from the pulsars in the globular cluster M53, pulsars in large measure line of cloud, and so on. And putting that all together and fitting a model for the Milky Way halo mass, we're able to find that if you take the total mass of the Milky Way halo, less than 10% with pretty high confidence is likely to be baryons, as compared with the cosmic average of about 16%. The Milky Way has fewer baryons than the cosmic average sort of baryon to dark matter ratio. This is, as it turns out, quite consistent with simulation of Milky Way sized halos, which suggest that they either don't accrete enough matter from the IGN or blow it out through various feedback processes. The second result, which I'm not going to dwell on at all, was the localized repeating FRB, which was remarkable in its entire ordinariness and like complete sort of unremarkability in that the host galaxy was modestly massive, modestly star forming, modest local DM, modest almost no local Faraday rotation, so on and so forth. A very unremarkable location for among the most active known repeating FRB sources. I'll skip right over that. We then discovered the first FRB sources within massive galaxy clusters. These two, this one over here, this little dot, which I think is evident over there, is a foreground star, but behind it is a relatively large galaxy. And this one down here as well, this host galaxy turns out to be less massive and a bit star forming, but nonetheless within a cluster. And the paper led by Liam, we're able to show that we actually have a detection of the intra-cluster medium along these sightlines, these ABL clusters. And what's particularly interesting about this is that we can start to use these measurements in sort of complementary sense to Sunyaev-Zeldovich measurements, X-ray emission measurements, in order to place constraints on the density profile, temperature, and potential asymmetries in these inter-cluster medium. So, for example, here you see 4 different comparable mass clusters from the illustrious TNG simulation as well. So the sort of range of possible dispersion measures you expect for different impact parameters, as well as the FRB measurements sort of overlaid in these four. This is only early days. We hope to find many more. But as it turns out, it's surprising nonetheless that we found any at all. Because galaxy clusters contain a negligible fraction of the star formation rate in the local universe. And yet, we had 2 out of the first sort of order 10 FRBs located within galaxy clusters. And we take it one step further, and work led by graduate student Kriti Sharma, we showed that one of these is an early type, entirely quiescent galaxy with no detectable star formation within it, likely a massive elliptical or a massive lenticular. And we're able to show that it's, for example, star formation history is consistent with an extremely old stellar population, showing it in a plot of stellar mass with star formation rate. It sits way down here. And this is very exciting because if we think that FRBs originate from neutron stars, we now need to have a way to make such a neutron star, indeed potentially a magneton, in an elliptical galaxy environment. Something like 0.03% of core collapse supernovae occur in elliptical galaxies. And we think, at least, that, well, it's accepted wisdom that most neutron stars in the Milky Way are made in core collapse supernovae. So moving on, so sort of sticking with this theme a little bit more, work led by Casey Law and Kriti as well, on our first sample of 11 well-characterized host galaxies seems to support this picture. So we were able to start to extract resolved star formation histories for these galaxies. And what we're finding is that the star formation history, so when the stars formed in these galaxies, are quite extended. The stars formed both a long time ago as well as very recently in some cases. Not just very recently, as may be expected if FRB sources are made in core collapse supernovae. And so we're actually able to start to fit a delay time distribution to these star formation histories, much like people do, for example, 1A supernovae, short and long gamma ray bursts, and so on. And we're finding preliminary evidence of an extended delay time distribution, where although short delay times from when the stars formed are favored, so we favor potentially more FRBs occurring close to when their progenitor stars formed, there is a long tail in the delay times as well towards extended star formation histories, such that indeed we might expect the progenitor of the FRB to have formed a few gigayear before the bursts were emitted. And this is kind of really becomes evident when you look at the distribution of the hosts we're finding in the sort of stellar mass star formation rate diagram, where the sort of sequence up here and these different redshift slices shows the sort of star forming main sequence that evolves, of course, with redshift. And we are finding some FRB sources of the star forming main sequence towards the cloud of red and dead galaxies that have ceased forming stars. So we are finding some FRB sources in galaxies like the first one I talked about that are not currently forming stars. And this leads us to speculate potentially on channels that form FRB sources that don't involve core collapse supernovae, and we're particularly excited about accretion-induced collapse of white dwarf neutron stars as a potential channel as well. So this is the case where we have, again, potentially shorter delay times being favored, but lower mass donor stars also leading to, in some cases, longer delay times. And there's plenty of work to be done on getting the rates right and so on, but we're exploring this, thinking to explore this in more detail. Work led by Miles Sherman is also really telling us, beginning to tell us a lot about the sources of the FRBs themselves, the emission mechanism. We're finding And this shows a subset of polarization measurements of our bursts and high time resolution data on the bursts. These aren't sort of simple, easy to characterize things. There are incredibly complex temporal structures, sometimes very interesting frequency structures as well. And if you squint, you can also see that the polarization properties of these bursts are incredibly rich. We see in some cases almost 100% linear polarization. In some cases, so the blue shows linear and the gold shows circular. You can see in this case, the sign of Stokes V flips across the burst. There's all sorts of fun behavior here that we're just starting to try and tease out. We're also trying to tease out how, for example, the Faraday rotation of these bursts is related to properties in the host galaxy, or indeed properties of the polarization. And we're just trying to make sense of this incredible richness of data at this moment. I like to show this because I think it's such a cool animation showing the projection of the polarization state of one of the bursts in the Poincare sphere, showing how one component, so this is going through in time, the dots show signal to noise ratio. One component starts over here, and you end up somewhere else in the second component. It's really fun data to try and think about and hopefully ultimately interpret. And so the prospects we feel are really bright for DSA-110. We're really finding this hugely rich sample of FRBs and FRB hosts. We're beginning an extensive follow-up program, but even the sort of subset and sample we've really characterized is telling us that FRBs originate from an incredible diversity of environments beyond that initial rapidly star-forming dwarf. We have Milky Way-like galaxies. We potentially do have some dwarf galaxies. We certainly have some giant elliptical type galaxies. We have a whole range of properties as well. This it may be a little bit of a surprise for us as well. I think that the field was previously moving in the direction of saying that most FRBs were related to star formation activity and recently formed progenitors, but we're now showing that we need to potentially consider multiple formation channels for FRB sources. There's plenty, and it's sort of a point that we debate a lot within the team, that several of the individual events are very interesting in their own right, and that was certainly not expected. For example, we have events like the galaxy cluster ones, the early type galaxies, events potentially from redshift greater than 1, events with undetectable hosts so far, events that are incredibly affected by plasma density fluctuations along the line of sight as well. And yes, there's that richness, I think, has been a real surprise to us at this point. We expect to complete the array later this summer and begin this extensive follow-up program, which we expect to really yield these transformational results, both on sources of FRBs as well as the distribution of matter along their sightlines. The team is also very excited about the DSA-2000 project, for which the DSA-110 is a technology sort of demonstrator in certain ways, certainly for the receivers and to a lesser extent the antennas. DSA-2000 is not just an FRB telescope, but will do FRBs. It's the next iteration in this process that will consist of 2,000 5-meter antennas located in Nevada, with the aim of first light in late 2026. The real sort of benefit of this paradigm of low-cost, small antennas deployed in copious amounts is the idea that we're going to attain really high survey speed. We can image a patch of the sky faster than other telescopes to the same depth. And in comparison with, for example, the upcoming square kilometer array or NGBLA, our survey speed is greater with almost comparable sensitivity. There are several science goals that I will not go into, but we will have an FRB survey that should deliver sort of tens of thousands of FRBs localized to few arc-second accuracy, starting to enable amazing science on intervening structures and the physical conditions. And so to conclude, I just want to leave you the following points. I framed this talk around the origins of FRBs, but set up the problem really as the need to localize them to individual galaxies. We are now doing this at a world-leading rate with the DSA-110, and we're already finding some very interesting things. First of all, a sort of neutron-star origin for FRBs, possibly a magnetar origin, is motivated both by physical arguments around the bursts, as well as the galactic magnetar source that emits an FRB-like burst. The DSA program is showing that FRB hosts are incredibly diverse. Some are very much not like the Milky Way at all, and this leads us to potentially call upon progenitor pathways for FRB sources, neutron stars that do not involve core collapse supernovae. And just to finish off, our early results on this program of understanding unseen cosmic baryons are proving to be very fruitful on the Milky Way halo, on the intra-cluster medium of nearby clusters, and hopefully in the near future on other structures along the line of sight to the DSA FRBs. And I'll leave you there. Thanks.
Okay, questions?
So what is the what is the astrophysical process that's the millisecond timescale? Can you explain the names of it?
There are certainly speculations. There are. I don't think I had. I think I deleted a slide that showed that for most of the history of this field, the number of sort of origin theories exceeded the number of bursts. But the speculations typically call upon some sort of a, what's the right word here? Let's call it an outburst from near the surface of a neutron star that leads to a plasma ejection that, at least along open field lines, may eventually transform into radiation. It becomes a charged star, transforms to radiation. Other models suggest that you drive these fast shocks into ejecta left by previous shocks, somewhat further away from the magnetospheres of these neutron stars. And then within there, you may call on maser, or something like that. This is all speculation, though. And there are issues with these various models. We've known about radio pulsars for more than 50 years now, and in some ways about the same distance towards understanding their emission as we are for FRBs.
Related question. So what are you feeling about the selection effects, right? So I think the models could happily reproduce microseconds and seconds if desired, but the observers are mostly looking at a millisecond because it's hard to get the electronics in a microsecond, and it's hard to do 2 seconds. So do you have a sense of how much of it is real and how that a millisecond is real, and that's just where it's easy to look?
Yeah. So it's a good point with the millisecond durations. It's not necessarily where it's easy to look. The discovery surveys, or at least the first larger samples of FRBs, sampled at about 50 microseconds. And so if the bursts really were 50 microseconds wide, they probably would have shown up. The typical DSA FRB is something like half a millisecond in duration, even though we're sensitive to much broader timescales. On the long side, we typically don't search beyond order 10 to 100 milliseconds, depending on the instrument. It tends to get really hard out there because a lot of terrestrial signals tend to mimic FRBs in those timescales. The effect of the dispersion becomes harder to determine. It's unclear what the rate is at long timescales.
Other questions? Quick comment about possible long durations. Wouldn't those be detectable with something like Cepheid phone?
Potentially, the issue is distinguishing them from interference. So a lot of interference on sort of 100 millisecond timescale is broadband and tends to show some frequency, time frequency structure. Really, we need imaging telescopes to show that they're in the far field versus
No, just the existence.
they've been detected. They're there, but we don't know about whether they're real or not.
Do you have any repeating FRBs with DSA-110? If so, what's the science that you can do with those sources that can't be done with other?
So we've localized a chime discovered repeater, but none of ours have shown repeat bursts. And that is in order 100 hours on sky per event. Yeah. It's unclear what that means because the statistics chime sample remain unclear. But yeah, I think that's if we were to discover some, then there's a few things we could do. We could say a lot about the local environment and how active it is or not. We could potentially talk about there's some really fun work that was discussed for some repeaters about potential superluminal motion at the source, behind a very sort of intermogenous scattering screen. You may be able to actually see that motion. Some work at these frequencies has been able to identify where the scattering is happening by looking at scintillation arcs in the Milky Way, for example. But yeah, beyond the sort of saying this is the galaxy, this is what the environment is, there's real speculation, like very distant FRBs that, like, imagine a lens repeating FRB. You can get incredible time delay measurements. But yes, that's the reality.
So the scenario of creating this box is quite interesting. So do you expect any like a smoking gun related to like an accretion companion or anything?
So that's a really interesting point. So if there is a rich ejector or potentially the companion is active and has a wind, we may expect to see an interesting sort of set of propagation effects local to the burst. For example, there was a really interesting work that Dr. Lee, a postdoc here, was involved with, which showed that a Black Widow pulsar showed Faraday conversion as the burst propagated through the wind of the companion, the magnetized wind of the companion. So this is conversion from linear to circular polarization and back, so generalized Faraday rotation. Those effects would be amazing to observe, and are certainly easier to see in repeating sources than one-off sources, although there are some signatures one might search for. Really, I think the smoking gun is if we're able to make a clear statement on the rates in completely quiescent galaxies, which we're beginning to be able to do.
So on that subject, come on, sir.
Different subjects, so maybe continue on that.
Oh, I was gonna say, so the confidence of the localizations, your beam is fairly big, your astrometry is being divided by signal noise.
Yes. Yeah.
But when you see a cluster of galaxies, for example, there are lots of star-forming galaxies usually around the outside.
Yes.
Ellipticals in the middle. The Milky Way has star-forming dwarfs orbiting it.
Yeah.
So, how confident are you? I mean, you're not able to localize that something is between spiral arms or in a galaxy, typically unless it's very nearby.
Mhm.
So, how confident are you in associating it with the elliptical or the spiral as opposed to some place in the elliptical or the spiral or satellite?
That's a really good point. So the first elliptical is indeed one of these ellipticals to the cluster. So we're very confident about that. The other ones, I would say, we need to do a bit more work to really tease out their And we have the observations now to tease out their local environments to understand whether they're isolated or in groups. I think they're likely in groups, but we need to be sure. But beyond that, really is a statistical argument based on the bulk star formation history of the galaxies. And then the question of why are we seeing FRBs from galaxies with such low star formation rates versus all the others with much higher star formation rates.
Right.
Do you have a slide or two on DQL, which was mentioned?
No, unfortunately. But yes, we are hoping to see and the sort of hints of millimeter emission, that bright millimeter emission detected during periastron.
You might want to mention what it is.
Sure.
It's
It's a young binary young star object, and it's an 18-bit day orbital period, and at periastron, the theory that the disks interact, and somehow, through a mechanism not fully understood, we observe really bright millimeter emission. And it's been seen as sort of snapshots with 3 different telescopes at 3 different times and sort of phase connected that way, but we just cracked periastron 2 days ago and hopefully do it another 18 days and so on.